Welcome to today's episode where we explore what may be the most significant astronomical discovery in human history. The James Webb Space Telescope has detected compelling evidence of life on a distant world, and the implications are staggering. Deep in the constellation Leo, 120 light-years from Earth, lies a planet that has captured the attention of the entire scientific community. This world, designated K218b, has revealed chemical signatures in its atmosphere that point to one extraordinary conclusion: we may no longer be alone in the universe. The data is unprecedented. Scientists have achieved 99.7% statistical confidence in detecting dimethyl sulfide, a molecule that on Earth is produced exclusively by living organisms. This isn't speculation or wishful thinking. This is rigorous science backed by the most advanced space telescope ever constructed. But K218b isn't just potentially inhabited. It might actually be more habitable than Earth itself, with a surface temperature of exactly 120 degrees Fahrenheit and conditions that could support liquid water across its entire surface. This super-Earth represents a new category of potentially habitable worlds. Today, we'll dive deep into this discovery. We'll examine the evidence, explore the technology that made it possible, and discuss what this means for our understanding of life in the universe. By the end of this presentation, you'll understand why December 2023 may be remembered as the moment everything changed for humanity. The story begins on a Tuesday morning in December when Gr. Niku Madhusudan at Cambridge University was analyzing data from the James Webb Space Telescope. He was studying infrared light that had traveled 120 light-years through space, carrying information about the atmosphere of K218b. What he saw in the spectroscopic data made him realize he was looking at something unprecedented. There, in the wavelengths of light filtered through an alien atmosphere, was a molecular signature that shouldn't exist on a lifeless world: dimethyl sulfide. This discovery wasn't made lightly. The detection required months of careful observation and analysis. The James Webb Space Telescope had to operate at the very limits of its capabilities, collecting photons of light so faint that they represented just a tiny fraction of the total light from the host star. The significance of finding dimethyl sulfide cannot be overstated. On Earth, this molecule is produced exclusively by living organisms. Marine phytoplankton create it as a byproduct of their metabolism. Certain bacteria and algae produce it as part of their normal biological processes. But no geological process, no chemical reaction, and no non-living system has ever been observed creating this molecule. The concentrations detected on KT218b are remarkable. They're not trace amounts that might be explained by unknown atmospheric chemistry. The levels are orders of magnitude higher than what would be expected from any non-biological process. This suggests that biological activity on KT218b isn't just present, it's thriving on a planetary scale. The statistical analysis of this discovery represents the gold standard in astronomical research. Scientists use what's called sigma detection levels to measure confidence. A 3 sigma detection, which corresponds to 99.7% confidence, is the threshold used to confirm the most important discoveries in modern science. This is the same standard used to discover new subatomic particles and confirm the existence of gravitational waves. But the dimethyl sulfide detection is just one piece of a larger puzzle. The James Webb Space Telescope has also detected water vapor, methane, and carbon dioxide in K218b's atmosphere. This cocktail of molecules paints a picture of a world where complex atmospheric chemistry is actively maintained by biological processes. Pound, understanding K218b, a world unlike any other. K218b challenges every assumption we've made about what a habitable world should look like. Located 120 light-years away in the constellation Leo, this planet orbits a red dwarf star in what astronomers call the Habitable zone, the region where liquid water can exist on a planet's surface. But K218b is no Earth twin. It's what scientists classify as a super-Earth, with 8.6 times the mass of our planet and 2.3 times its radius. This massive size creates surface gravity nearly 3 times stronger than Earth's. A person weighing 150 pounds on Earth would weigh over 400 pounds on K218b. Initially, this might seem like a disadvantage for habitability. However, the planet's massive size actually provides several benefits that make it potentially more habitable than Earth. The intense gravity holds the atmosphere in place with an iron grip, preventing it from bleeding away into space like Mars lost its atmosphere billions of years ago. Even violent stellar flares from the host star cannot strip away K218RTB's thick atmospheric envelope. The planet's atmosphere is dominated by hydrogen and helium, creating conditions completely alien to anything in our solar system. On Earth, hydrogen makes up less than 1 part per million of our atmosphere. On K2-18b, hydrogen comprises the vast majority of the atmospheric envelope, creating a unique environment that could support entirely different forms of life. This hydrogen-rich atmosphere creates what scientists call a controlled greenhouse effect. Instead of cooking the planet like Venus, the hydrogen acts as a perfect insulator, maintaining stable temperatures across the planet's surface. The thick atmosphere redistributes heat so efficiently that even the night side of the planet, which never sees sunlight due to tidal locking, remains warm enough for liquid water. The temperature readings are particularly striking. K2-18b maintains a surface temperature of exactly 120 degrees Fahrenheit. This isn't just warm enough for life, it's optimal for biological processes. Laboratory experiments have shown that many biochemical reactions proceed most efficiently at temperatures around this range, while remaining cool enough to prevent the breakdown of essential biological molecules. Pound, the hydrogen ocean, a new type of habitable environment. Beneath K2-18 atmosphere lies an ocean unlike anything in our solar system. Computer models suggest this isn't just water, but a hydrogen-enriched solution that could extend hundreds of miles deep. This hydrogen ocean represents a fundamentally new type of environment where life might thrive. The ocean exists because of the planet's unique atmospheric chemistry. The hydrogen atmosphere doesn't just float above the surface, it dissolves into the liquid water, creating a solution that remains stable across a much wider range of temperatures and pressures than pure water. This hydrogen water mixture can exist as a liquid from near freezing to over 300 degrees Fahrenheit, giving life an enormous range of conditions in which to develop. This hydrogen ocean solves several major challenges for life on exoplanets. First, it acts as a massive atmospheric reservoir. As hydrogen is lost to space over geological time, more dissolves out of the ocean to replace it, potentially maintaining a stable atmosphere for trillions of years. This long-term stability is crucial for the development of complex life. Second, the hydrogen in the water acts as a natural pressure buffer. On Earth, the deepest parts of our oceans are under crushing pressure that limits the types of life that can survive there. But on K2-18b, the hydrogen dissolved in the water maintains more moderate conditions, even at great depths, potentially allowing life to thrive throughout the entire water column. Perhaps most remarkably, the hydrogen ocean opens up possibilities for entirely new forms of metabolism. Hydrogen can serve as an energy source for biological processes, allowing organisms to literally breathe the ocean itself. On Earth, some bacteria can metabolize hydrogen, but they're limited by its scarcity in our atmosphere. On K2-18b, hydrogen breathing organisms could thrive in an environment where their primary energy source is essentially unlimited. The depth of K2-18b's ocean remains uncertain, but models suggest it could be hundreds of miles deep, far deeper than any ocean on Earth. This vast volume of liquid water mixed with hydrogen could harbor ecosystems of unimaginable complexity and diversity. The stable temperature and pressure conditions could allow life to evolve in ways that are impossible on Earth, potentially reaching levels of sophistication that we can barely comprehend. The James Webb Space Telescope, humanity's most powerful eye in space. The discovery of life on K2-18b would have been impossible without the James Webb Space Telescope, humanity's most ambitious space science project. Positioned 1 million miles from Earth at a gravitational balance point called L2, Webb exists in perpetual darkness, its massive sun shield blocking heat and light from our star to keep its instruments colder than the surface of Pluto. Webb's primary mirror stretches 21 feet across, nearly 3 times wider than the Hubble Space Telescope. But size alone doesn't explain Webb's revolutionary capabilities. The mirror consists of 100 hexagonal segments, each coated with a microscopic layer of gold that reflects infrared light with unprecedented precision. When these segments work together, they create a mirror so perfectly aligned that it could theoretically detect the heat signature of a bumblebee on the moon. The telescope's focus on infrared light is crucial for detecting life on distant worlds. Infrared radiation is invisible to human eyes, but it carries the fingerprints of molecules in planetary atmospheres. When planets pass in front of their stars, a tiny fraction of starlight filters through their atmospheres before reaching Earth. Different molecules absorb specific wavelengths of infrared light, creating unique signatures that Webb can detect with extraordinary sensitivity. The challenge of detecting these molecular signatures is almost incomprehensible. Imagine trying to identify a specific voice in a crowd of millions while that crowd is shouting next to a jet engine. The star K2-18 is billions of times brighter than the planet orbiting it, yet Webb can pick out the faint infrared signatures of molecules in the planet's atmosphere with pinpoint accuracy. Webb accomplishes this through advanced coronagraph technology originally designed to block starlight and reveal objects hiding in stellar glare. Sophisticated image processing algorithms subtract the overwhelming brightness of the star, leaving behind the faint infrared signatures of atmospheric molecules. It's like using a precision filter to remove the roar of a waterfall so you can hear a whisper underneath. The detection of dimethyl sulfide on K2-AQB required Webb to operate at the absolute limits of its capabilities. The molecule produces an infrared signature so faint that it took multiple observations over several months to confirm its presence. Each observation captured just a few photons of light that had traveled 120 light-years through the vacuum of space, carrying information about life on another world. But Webb's most remarkable achievement might be its ability to measure temperature with incredible precision across interstellar distances. The telescope detected that K2-18b maintain a surface temperature of exactly 120 degrees Fahrenheit, accurate to within a few degrees. This level of precision in measuring the environment of a world 120 light-years away represents one of the most remarkable technical achievements in the history of astronomy. Pound, the chemistry of life, reading the atmospheric fingerprint. Every molecule tells a story, and the James Webb Space Telescope has become expert at reading these molecular narratives written in starlight. When light from K2-18 star passes through the planet's atmosphere, it creates what astronomers call a transmission spectrum, a cosmic fingerprint that reveals the planet's atmospheric composition with extraordinary precision. The process of analyzing these atmospheric fingerprints is like cosmic archaeology. Each type of molecule absorbs light at specific wavelengths, creating dark lines in the spectrum that Webb can detect and analyze. Oxygen creates one pattern, water vapor another, methane a third. When Webb analyzed K2-18b's spectrum, it found something unprecedented, a combination of molecules that could only be explained by active biological processes. The atmospheric fingerprint reveals a world in chemical disequilibrium. In a lifeless atmosphere, chemical reactions would eventually reach equilibrium, creating a stable mixture of gases that doesn't change. But K2-18b's atmosphere contains combinations of molecules that should react with each other and disappear, yet they persist in large quantities. This chemical imbalance is the signature of life actively pumping gases into the atmosphere. On Earth, our atmosphere shows similar chemical disequilibrium. We have both oxygen and methane in our atmosphere, gases that should react with each other and disappear. The only reason they persist is that living organisms constantly produce both gases, maintaining the chemical imbalance that characterizes a living world. K2-18b shows the same type of chemical disequilibrium, strongly suggesting that life there is actively shaping the planet's atmospheric chemistry. The detection of dimethyl sulfide represents the strongest evidence for this biological activity. The precision required to detect these molecular signatures is staggering. Webb must measure the absorption of light at specific wavelengths to an accuracy of 1 part per million, detecting molecular signatures so faint that they represent just a tiny fraction of the total light from the star. The data processing involves some of the most advanced algorithms ever developed, with artificial intelligence systems analyzing millions of data points to extract signals that would be invisible to human observers. Pound, the perfect temperature, 120 degrees Fahrenheit. Temperature is everything when it comes to life, and K2-18b appears to have hit the cosmic jackpot. The planet maintains a surface temperature of exactly 120 degrees Fahrenheit, warm enough to drive rapid chemical reactions and maintain liquid water, yet cool enough to prevent the breakdown of complex organic molecules. This temperature isn't just habitable, it's optimal for life as we understand it. At 120 degrees, water exhibits properties that are ideal for supporting biological processes. The liquid is warm enough to dissolve a wide range of chemical compounds, creating solutions that can efficiently transport nutrients and waste products. The temperature accelerates biochemical reactions, allowing metabolic processes to proceed at rates that support active life while remaining slow enough to maintain stable molecular structures. The significance of this temperature extends beyond simple chemistry. On Earth, our most extreme life forms thrive at similar temperatures. Deep-sea hydrothermal vents, where temperatures reach 120–150 degrees Fahrenheit, host some of our planet's most remarkable organisms. These environments support life forms that use chemical energy instead of sunlight, creating ecosystems completely independent of surface conditions. The discovery that K218b maintains this optimal temperature suggests that similar chemosynthetic life might be common throughout the universe. If organisms on this distant world are thriving at 120 degrees, they might have evolved biochemical pathways similar to Earth's extremophile organisms, but on a planetary scale. The temperature is maintained through K218b's atmospheric greenhouse effect, but it's a controlled and stable greenhouse, unlike the runaway heating that makes Venus uninhabitable. The planet's hydrogen-rich atmosphere acts like a planetary thermostat, trapping just enough heat to maintain comfortable conditions while preventing the extreme temperature fluctuations that characterize many other worlds. This temperature stability is crucial for the development of complex life. On Earth, temperature variations create stress on living organisms, forcing them to adapt to seasonal changes or develop complex physiological mechanisms to regulate their internal temperature. On KT218b, the stable temperature would allow organisms to invest energy in growth, reproduction, and evolution rather than survival. Perhaps most remarkably, laboratory experiments have shown that 120 degrees Fahrenheit is optimal for the formation of complex organic molecules. This temperature range allows for the chemical reactions that create life's essential building blocks while preventing the thermal breakdown that would destroy them at higher temperatures. K218b isn't just maintaining the right temperature for existing life, it's providing the perfect conditions for life to emerge and evolve in the first place. Pound the host star, K2118's billion-year promise. K218 is not a star like our sun, it's a red dwarf, smaller, cooler, and dimmer than the star that lights our world. But this seemingly modest star might be the most important type of star in the universe when it comes to supporting life. While our sun will eventually expand into a red giant and destroy all life on Earth. K2020 red 2020 red dot 18 will burn steadily for trillions of years, providing stable energy for eons that dwarf the entire age of the universe. Red dwarf stars make up about 75% of all stars in the galaxy, making them the most common stellar type in the cosmos. They're typically less than half the mass of our sun, and they burn their nuclear fuel so slowly that they can maintain steady energy output for periods longer than the current age of the universe. While our sun has a lifespan of about 10 billion years, red dwarfs like K218 can shine for up to 10 trillion years. This incredible longevity has profound implications for life. On Earth, complex life took nearly 4 billion years to evolve from simple bacteria to the diverse ecosystems we see today. If life on K218b has had even a fraction of the time available around its red dwarf star, it could have reached levels of complexity and sophistication that make Earth's biosphere seem primitive by comparison. The gravitational relationship between K218b and its star has created tidal locking, where one side of the planet always faces the star while the other remains in perpetual darkness. This might seem disadvantageous, but the planet's thick atmosphere redistributes heat so efficiently that both sides maintain comfortable temperatures. The result is a world with permanent day and night sides, each offering different environments for life to explore and exploit. Pound atmospheric dynamics, a living atmosphere. The atmospheric chemistry of K218b reads like science fiction, but every measurement confirms that this alien world maintains an atmosphere more complex and dynamic than while Earth's atmosphere is a relatively simple mixture of nitrogen and oxygen, K218b's atmosphere is a sophisticated cocktail of molecules that create conditions both alien and surprisingly conducive to life. Methane swirls through hydrogen clouds in concentrations that tell a story of active biological processes. On Earth, methane is produced by everything from bacteria in swamps to the digestive processes of animals. It's one of the most common products of biological activity, but it's also highly reactive, breaking down in the atmosphere within a few decades. The fact that Webb detected substantial amounts of methane on KT18b means something is actively producing it in vast quantities, but methane on KT18b serves purposes beyond just being a byproduct of life. In the hydrogen-rich atmosphere, methane acts as a crucial component in a complex carbon cycle, helping to regulate the planet's temperature and atmospheric chemistry. Organisms on KT18b might actually breathe methane, using it as an energy source in ways that would be impossible on Earth's oxygen-rich world. The atmospheric pressure on K218b creates conditions that seem almost magical. At certain altitudes, the temperature and pressure combine to compress carbon atoms into microscopic diamond crystals. These diamonds form in the upper atmosphere and rain down toward the surface, creating a constant shower of precious gems. To any life forms on K218b, these diamonds would be as common as raindrops are to us. Carbon dioxide adds another layer of complexity to the atmospheric chemistry. Unlike Earth, where Kotwo is a trace gas, K218b's atmosphere contains substantial amounts that interact with hydrogen and methane in intricate chemical reactions. This three-way molecular dance creates conditions that could support entirely different forms of photosynthesis than anything found on Earth. The planet's atmospheric dynamics are driven by its tidal locking, where one side always faces the star while the other remains in perpetual. This creates massive atmospheric currents that carry heat, moisture, and chemical compounds from the day side to the night side. These planetary scale winds constantly mix and redistribute atmospheric chemistry, creating stable conditions across the entire surface. The thick atmosphere also serves as a natural radiation shield. Red dwarf stars like K218 occasionally produce powerful flares that could sterilize planetary surfaces. But K218b's dense hydrogen atmosphere absorbs and deflects this harmful radiation, protecting any surface life from lethal energy bursts that would be devastating to Earth-based organisms. Pound, the methane mystery, evidence of planetary scale biology. Methane should not exist in significant quantities in K218b's atmosphere, yet the James Webb Space Telescope has detected it in concentrations that can only be explained by biological activity on a truly planetary scale. This simple molecule, one carbon atom surrounded by 4 hydrogen atoms, is highly reactive and breaks down quickly when exposed to ultraviolet radiation. Its persistent presence in K218b's atmosphere points to continuous production by living organisms. The methane concentrations detected by Webb are extraordinary. They're orders of magnitude higher than what could be produced by any known geological process. On Earth, geological sources like volcanic outgassing produce only tiny amounts of methane compared to biological sources. The levels detected on K218b suggest that biological methane production there dwarfs anything seen on Earth. This isn't just evidence of life surviving on an alien world, it's evidence of life thriving and fundamentally altering atmospheric chemistry on a global scale. The organisms producing this methane must be incredibly abundant and productive, creating biological signatures strong enough to be detected across 120 light-years of space. The methane mystery deepens when we consider K218b's unique atmospheric environment. In the planet's hydrogen-rich atmosphere, methane can serve multiple biological functions that are impossible on Earth. It can act as both a carbon source and an energy source for organisms, potentially supporting ecosystems where life forms breathe methane and metabolize. Statistical confidence, the gold standard of scientific certainty. In the world of science, certainty is rare and precious. Scientists speak in probabilities, confidence levels, and margins of error. They hedge their statements and acknowledge uncertainty as an inherent part of the scientific process. But when the James Webb Space Telescope data on K218b was analyzed, the numbers told a story so clear that even the most conservative scientists couldn't ignore it. There was a 99.7% chance that the dimethyl sulfide signal was real. To understand what this level of confidence means, consider flipping a coin 1,000 times. The probability of getting heads or tails on any single flip is 50%, but the probability of getting heads 997 times out of 1,000 flips is so vanishingly small that it would never happen by chance in the entire history of the universe. That's the level of statistical confidence scientists have in the detection of life, indicating molecules on K218b. This confidence level comes from sophisticated statistical analysis called sigma detection. In particle physics and astronomy, scientists use sigma levels to measure how likely it is that a signal represents a real discovery rather than random noise or A3. Sigma detection means there's a 99.7% chance the signal is real and only a 0.3% chance it's a false alarm. This is the same statistical threshold used to discover new subatomic particles, confirm the existence of gravitational waves, and validate the most important discoveries in modern science. When the Higgs boson was discovered at CERN, it met the 3 sigma standard. When LIGO detected gravitational waves from colliding black holes, it exceeded this threshold. The detection of biosignatures on K218b meets this same rigorous standard. Reaching this level of confidence for an exoplanet atmosphere required unprecedented precision and multiple independent confirmations. The dimethyl sulfide signal is extraordinarily faint, just a few parts per billion in the infrared spectrum. To detect it reliably, Webb had to measure wavelengths of light to an accuracy of 1 part in 10 million, equivalent plus to measuring the width of a human hair to the precision of a single atom. The analysis involved multiple independent observations over several months, each confirming the presence of the dimethyl sulfide signature at different wavelengths. Different instruments on Webb detected the same molecular fingerprint, providing redundant confirmation of the discovery. Advanced computer algorithm of data points searched for systematic errors, instrumental artifacts, or contamination that could explain the signal. None were found. The statistical analysis also considered alternative explanations. Could unknown atmospheric chemistry produce dimethyl sulfide through non-biological processes? Could the signal be contamination from Earth or artifacts from Could it be statistical noise that happened to mimic a biological signature? Each possibility was tested and ruled out with mathematical precision. The 99.7% confidence level represents more than just statistical analysis. It represents the collective weight of evidence from multiple independent measurements, theoretical considerations, and exhaustive testing. This level of certainty is as reliable as any fact in modern science, comparable to our confidence in the existence of DNA, the validity of Einstein's relativity, or the age of the universe. Pound the 120 light-year journey. Messages from the past. The distance to K218b is both impossibly vast and tantalizingly close. At 120 light-years away, the light carrying information about this world's atmosphere left the planet's surface when Theodore Roosevelt was President of the United States. It's a distance, so enormous that our fastest spacecraft would take over 2 million years to reach it, yet it's practically next door in cosmic terms. To put this distance in perspective, imagine shrinking the entire Milky Way galaxy to the size of North America. Earth would be smaller than a grain of sand, and K218b would be another grain of sand about the width of a small town away, in a galaxy containing over 400 billion stars. K218b is close enough that we can study its atmosphere in unprecedented detail. The journey of light from K218b to Earth represents one of the most remarkable information transfers in human history. The photons detected by the James Webb Space Telescope carry molecular fingerprints that traveled through the vacuum of space for 120 years. When that ancient light finally reaches Webb's mirrors, it's so faint that the telescope must collect photons for hours just to detect the presence of a single type of molecule in the planet's atmosphere. Earth was just beginning its industrial revolution. We're seeing the breath of alien life from the past, preserved in starlight that has crossed the cosmic void. The implications of detecting biosignatures at this distance are staggering. If we can identify life on K218b from 120 light-years away, the biological activity on that world must be enormous. The organisms producing dimethyl sulfide aren't just surviving in isolated pockets, they're thriving on a planetary scale, creating atmospheric signatures so strong they can be detected across interstellar space. Distance also works in our favor for future observations. While K218b is too far away for any conceivable human mission with current technology, it's close enough for detailed study with increasingly powerful telescopes. The upcoming Extremely Large Telescope, with its 130-foot mirror, will be able to analyze K218b is gifted atmosphere with unprecedented precision, potentially detecting dozens of different biosignatures and revealing details about the planet's biochemistry that are currently beyond our reach. The 120 light-year distance places K218b within what astronomers call our local galactic neighborhood. This region contains several thousand star systems, many of which likely harbor planets of their own. If life exists on KT218b, it suggests that our cosmic neighborhood might be teeming with living worlds, each developing unique biospheres and following distinct evolutionary paths. Perhaps most intriguingly, the distance means that if intelligent life exists on K218b, they could potentially be detecting signs of life on Earth right now. The radio signals we've been broadcasting into space for the past century are just reaching their stellar neighborhood, potentially announcing our presence to any civilization advanced enough to detect. We might not just be discovering life on a distant world, we might be making first contact across the vast darkness between stars. Pound coronagraph technology, blocking starlight to reveal hidden worlds. The challenge seemed impossible. How do you photograph a firefly hovering next to a searchlight from 1,000 miles away? That's essentially what the James Webb Space Telescope needed to accomplish to detect planets like K2218b. The star K2218 is billions of times brighter than the planet orbiting it, creating glare so intense that it would normally make planetary detection completely impossible. The solution came from decades of experience studying our own sun. Astronomers have long used devices called coronagraphs to block the sun's blinding light and observe its corona, the faint outer atmosphere normally invisible against the star's brilliant surface. Webb's engineers adapted this technology for exoplanet detection, creating what might be the most sophisticated light blocking system ever devised. Webb's coronagraph works like a carefully engineered eclipse. A series of precisely shaped masks and mirrors block the star's light while allowing the much fainter light from orbiting planets to pass through. But this isn't simply a disk blocking the star, it's a complex system of multiple masks, each designed to eliminate specific types of light contamination. The tolerances are so precise that a misalignment of just a few billionths of a meter would ruin the entire observation. The coronagraph's performance is measured in contrast ratios, how much fainter the planet is compared to its star. For K218b, this ratio is approximately 10 billion to 1. To put this in perspective, imagine trying to spot a single candle burning next to the brightest stadium lights during a night game while looking through a telescope from the opposite side of the country, but blocking starlight is only half the battle. Once the starlight is removed, astronomers must deal with what they call speckles, tiny imperfections in the telescope's optics that create false signals mimicking planets. Advanced computer algorithms analyze these speckles in real time, using artificial intelligence to distinguish between genuine planetary signals and optical artifacts. The processing power required is equivalent to analyzing millions of photographs simultaneously to find one specific pattern. The coronagraph's success depends on Webb's unprecedented stability in space. The telescope must maintain its position with an accuracy of milliarc seconds, equivalent to holding a laser pointer steady enough to hit a dime on the moon. Any vibration, drift, or movement would blur the delicate observations and make planetary detection impossible. Perhaps most remarkably, Webb's coronagraph doesn't just block light, it actively shapes it using wavefront correction technology. The system constantly adjusts incoming light to create perfect conditions for planetary detection. It's like having a cosmic lens that can bend and focus light in ways that reveal hidden worlds orbiting distant stars. The relationship between planetary mass and habitability is complex and counterintuitive. On Earth, we've grown accustomed to thinking of our planet's size as perfect for life, large enough to hold onto an atmosphere, small enough to maintain comfortable surface gravity. But 218b demonstrates that significantly more massive worlds can provide advantages that Earth-sized planets cannot match. The planet's massive size creates surface gravity nearly 3 times stronger than Earth's. While this might seem disadvantageous, the intense gravity serves crucial functions that enhance long-term habitability. The strong gravitational field holds onto the planet's atmosphere with tremendous force, preventing atmospheric escape that has plagued smaller worlds like Mars. Even the most violent stellar flares from the host star cannot strip away K218b's thick atmospheric envelope. This gravitational advantage extends to water retention. On Earth, we gradually lose water to space through atmospheric escape, where water vapor in the upper atmosphere is broken apart by solar radiation, allowing hydrogen to drift away forever. K218b's powerful gravity prevents this loss, creating a world where water can accumulate over billions of years rather than slowly disappearing into space. The planet's mass also influences its internal structure in ways that benefit habitability. The intense pressure at K218b's core likely prevents the formation of a solid, iron core like Earth's. Instead, the planet may have a water-ice core surrounded by layers of liquid water hundreds of miles deep. This creates a planetary ocean that dwarfs all of Earth's oceans combined, providing an enormous environment for life to develop and diversify. K218b's mass places it precisely in what astronomers call the super-Earth sweet spot, large enough to maintain thick atmospheres and deep oceans, but not so large that it becomes a gas giant like Neptune or Jupiter. The boundary between rocky super-Earths and gaseous mini-Neptunes appears crucial for habitability, and K218b sits exactly in this optimal range.